Yeah, so it's the last talk of the day, so I've tried to make this a little bit shorter, hopefully, than the time allotted, and also pretty high level so that everyone can take away something. This is a relatively recently posted thing, so this is posted to the archive on Friday and completed rather recently over the summer with this talented undergraduate from UToronto, Drax Roni, and then my advisor, Ike Twong at MIT. So obviously it relates to quantum signal processing, which you've seen sort of appear, as well as quantum singular value transformation and some of the other talks, but here sort of focusing on these algorithms individually and hopefully introduce some techniques that people find entertaining. Cool. So I'm going to start off just with a motivation slide for sort of what I've been thinking about recently and what I enjoy in quantum algorithms, and maybe this will figure itself out. Oh, okay. Cool. Maybe I have to be clicked on the screen or something. Yeah, so we all sort of know, I mean, this is why we're here. Quantum algorithms are pretty tough to design and to interpret. It seems like when they do appear, they're pretty strange, and we don't have a lot of them. And there's some good questions as to why this is, right? Is this something that's insurmountable, or is it something that is a growing pain of the field? So despite a lot of beautiful work out in the world of quantum programming languages that's happened since about 2000, most of the time we still reason about quantum algorithms at a pretty low level. Again, this is geared towards hardware. And this seems sort of difficult, and it might make it increasingly difficult to try to design algorithms and devise algorithms that really look interesting and have sort of easily interpretable properties. So something I was thinking about during this work, in addition to sort of trying to devise a new quantum algorithm, I also care really about quantum algorithm design and seeing what aspects from the world of classical programming language theory, its techniques and abstractions can be used in the design of quantum algorithms. And to just give a visual depiction of what it feels like to design a quantum algorithm, most of the time this is sort of the feeling that I have. So the goal is to remove a little bit of the mystery and hopefully make it more like an engineering role with a salary rather than a hut on the top of the mountain. So the overview of this is I'm going to talk about an algorithm that's at least close to my heart and has appeared a lot in a bunch of different subfields. This is quantum signal processing. I'll also talk about singular value transformation, but most of the things that I'm going to talk about really only deal with the QSP, which is the single qubit sort of core of that algorithm. And then I'm going to try to make an argument that what I'm going to call function-first algorithmic design is not only desirable, but is actually sort of not immediately obviously possible, and that if we could achieve it, this would be great, and hopefully that you can turn this desire into something like a formal problem. So I'll set up that problem, and then I'll sort of sketch out our solution, show that not only is this sort of something that's helpful in the design of quantum algorithms, but that it actually saves you some query and space complexity in a lot of cases. And I'm also going to couple it to some questions and some techniques in functional programming languages, which I think have a lot to say about how we think about the design of composite quantum algorithms. And at the very end, I also have a link to a Python package that I wrote with all of the other co-authors that you can sort of implement examples from this paper, as well as design your own composite quantum algorithms built of these things that we're going to call gadgets. Cool. So starting with QSP, you don't really need to know that much about QSP for this talk, besides that it's a relatively simple algorithm with a nice alternating ansatz. So the idea here is that these boxes are something like quantum gates, and the different colors represent sort of gates of different forms. So one of the gates, which is this S gate, you don't know, but you have repeatable query access to. And the other ones, these white gates, you do know, and you get to choose them. And by sort of programming and turning all the knobs on these white gates, the result of this algorithm, when you give it some repeated unknown black gate, will be something which depends non-linearly and very specifically on sort of properties of that black gate. So normally, these gates are considered to be orthogonal rotations or rotations about orthogonal axes. And this is not so important to understand here, but just understand that there's sort of a lot of structure in these circuits. And it's sort of very well understood exactly the types of transformations that are possible, how to find these phi parameterizations efficiently, and all sorts of things like that. And these algorithms have really found their own in unifying and sort of helping to explain a lot of different quantum algorithms' behavior through their use in basically spectral mapping. So you give them a linear operator that's suitably encoded within a larger unitary, and then sort of based on some techniques that come just from the single qubit phenomenon, you can really apply any function you want up to some mild constraints to the spectrum of that operator. And it turns out that a lot of problems really look like this, like matrix inversion, et cetera. And so if you can do things like HHL, which is BQP complete, you can really describe a lot of algorithms using a technique like this. And the great thing about them is that they end up being pretty space and query efficient. They have a lot of desirable properties depending on the function that they implement. And so it seems like these are sort of a nice place to start when you want to talk about a very flexible and very interpretable quantum algorithm. So oftentimes, you're really just thinking about the function that you want to apply, as well as sort of input assumptions and how you get these mysterious block encodings that everyone is talking about. But the point I want to emphasize is just that these are sort of very functionally interpretable algorithms. And specifically what I mean by that is that, for the standard QSP ansatz, you just have that a matrix element ends up being a polynomial in some scalar that parameterizes your unknown gate. So those black boxes before contain a scalar which parameterizes basically the angle of rotation, and you can apply a polynomial to that matrix element. So along with this sort of functional interpretability, so you can choose P really nicely, it sort of seems like if I gave you protocols for achieving a bunch of different functions, say, two one-variable functions and one two-variable function, then it seems like it shouldn't really be that difficult to determine the protocol that achieves something like the composition of these two functions. So H applied to f of x and g of y. So, I could do this classically. I could, let's say that these are all polynomials. I compute this big composition and ends up being a polynomial as long as it satisfies the constraints that QSP desires. Maybe then I use all these methods to compute the phis. But I don't just want that. I really want this protocol to use these subroutines here, f and g, in a contiguous way. So if I just gave you, a black box superoperator that took in a unitary and output a unitary that corresponded to this function f, I should be able to use this without knowing what that function f is in sort of my algorithm. So sort of the goal here is that, if you have a bunch of building blocks that are functionally interpretable, maybe in a similar way to QSP, it sort of seems that you should be able to pass these things around, these functions around as sort of first-class objects. This is a common thing in computer science and especially functional programming languages. And we want to see sort of if QSP or algorithms like it admit a similar idea. And then maybe we'll talk about sort of why this can be useful. And just sort of visually, when we think about this, instead of thinking about all these equations, maybe you can just think about boxes. They have inputs and outputs. And so, if you plug an input into an output, these are very easy to reason about. And you can convert it back into functions at the end of the day. This notation will sort of appear a little bit later. And I just want to make clear that these boxes are different than the boxes you saw previously. Those were gates, which act on quantum states and return quantum states. And these are superoperators, which take in unitaries and return unitaries. So the way that we'll think about QSP now is that it takes an unknown unitary as input and it returns a unitary as output. So in that sense, time still is, time is not quite moving left to right in this instance here, because these are sort of recursively embedding these functions. Cool. So the problem with doing this immediately is that if I gave you a QSP protocol and every time it says that it wants an oracle, you feed it in the output of another QSP protocol, the functions are not going to be composed in the way that you'd expect. And this is due to sort of how the ansatz is chosen. These x and z rotations have some additional things going on in the off-diagonal elements. And even though you usually only care about the on-diagonal element, here it sort of starts to make problems. And really this comes down to the fact that it expects rotations about a single fixed axis, and it doesn't produce them as output in general. And this problem really only gets worse if you try to do standard qubitization arguments, or if you try to use, say, multiple different oracular inputs, which may in general not only be not rotations about the x-axis, but may be rotations about arbitrary axes. And it's just not so clear how you can maintain this functional interpretability of matrix elements. Yeah.
What is the bad proposal? Is it to implement the entire previous the entire F algorithm in the place of the black box of the H?
Yeah. So every time you would have just had an oracle, you just call whatever the F circuit was, and you stick it into that slot.
That's the stronger.
Yeah. So that's something that you think might work, but doesn't work because of just how the QSP ansatz. But the point is that you really don't want it to be any less efficient than that, because if you start, if you pay exponentially queries, or you have to do some sort of measurement or something non-coherent, you sort of lose all the gain. So what we really want to do is we don't want to learn anything about what F happens to be. We just need to make sure that it plays with circuit composition in the way that respects functional composition. So there's two levels in QSP. There's the functional level and the circuit level, and we want to be able to reason purely at the functional level, and then ensure the preimage is good.
I guess maybe more like a practical issue, is it possible that if you do this as a black box, you could get a suboptimal circuit, and maybe if you directly do QSVT and the target function, you can get a better circuit?
Yeah, so I'll talk about the efficiency in a little bit, but obviously, let's say you have a function that approximates a polynomial, and then you have a function which approximates the inverse of that polynomial on some range in which it's invertible. So you get something that looks like x on the output, right? Obviously, the function x should be implementable with like a single query. So there are functions for which it's not a good idea to do this, and in fact, there's many paths to any given function, but there are ones for which it is efficient, and for which basically the function is not close to any lower degree polynomial. Yeah.
But if you think about this as a level of block encodings and not just X rotations, then it produces the same type of output as the input. So then this is not an issue that you say.
Yeah, so when we're thinking about block encodings, you still have the issue because within the singular vector subspaces that are preserved by QSVT, if you were to just apply the oracles in the same sort of flat way without, say, post-selecting on any of the right blocks, these off-diagonal elements in general won't be like purely imaginary over the arguments of the input, and this will sort of still cause issues. I've thought about this for QSVT, and it really does seem like this problem is still inherited if you don't want to have extra ancilla that you're selecting on. But it's a good question, yeah.
Is it possible to give a simple example of like where this wouldn't work as you wanted to?
I mean, if you take the result of a QSVT protocol, this is some big unitary and it has some extra qubits which allow you to select to the right block. And if you were to plug in this block encoding where another protocol would have expected the same block encoding and used the phases for a different protocol, you still get something which block encodes a function. It just ends up not being the composition of the functions of the two QSVT protocols. And this is basically because within each of these singular vector subspaces, and I have maybe some plots about this. So within each of these subspaces, sort of, you may have dependencies. Basically, when this xi goes to a p of xi, and you have some sort of q of xi on the off diagonal, this q of xi is not necessarily a purely imaginary function for arbitrary p.
But if you just add one more ancilla qubit, then it's resolved, right?
Well, we don't want to add another ancilla qubit for our purposes. I mean, you could also do things with LCU. But yeah, I agree. So one of the things that we're going to learn later in this talk is that there are sort of many ways to achieve multivariable block encodings. And it seems like in different regimes, they can have benefits and drawbacks. But yeah, does that answer your question for now? Yeah. So yeah, for the moment, these QSP protocols sort of aren't, you can't pass them around as data. So these superoperators sort of can't be immediately fed into the open slots and these other superoperators to achieve functional composition in the way that you'd like under these types of space restraints that we really want, which is that if possible, we'd like to do this almost entirely flatly so that we're not introducing any extra space. And this is going to be because there's other methods for doing this type of thing. So yeah, the benefits, or why would we sort of deal with this? Oftentimes, right, if you can get away with dealing with less complicated components, once you've computed it, you would like to be able to reuse it in other places. This is common in classical signal processing. If you have some, guitar pedal and you just want to plug a bunch of them together, you'd like them to, you don't want to have to redesign sort of the composition of the two. And we also have a lot of nice properties of QSP as opposed to other methods. It has some pretty good space efficiency, nice dependence on the infinity norm of the function that you're embedding, and we know a lot about it numerically. But we also know that even on the numerical side, you want to sort of try to keep the degrees of things as low as possible, just for stability. We also know sort of the general multivariable analogs of QSP, so when you just try to do these circuits with multiple oracles are generally hard to describe in a functional way. But multivariable functions are obviously sort of ubiquitous in a lot of direct applications. So yeah, this is the slide I had up before. So we're talking about QSP during this talk, but you can also imagine sort of the lifted variant of this, which recreates something that looks similar to QSP in each of these preserved subspaces, and you can view them as either a consequence of the CS decomposition or this older result called Jordan's lemma. But really, sort of for a lot of operators in a lot of cases, sort of the things that you can do in these two-dimensional subspaces it really sort of describes the action of the algorithm. And then nothing that we do is going to sort of violate this property. Yeah, so the definition of a gadget right now, it's pretty agnostic to QSP. We'll talk about that later, but really it's just it's a unitary asterisk, so it can be allowed to be slightly non-unitary. Superoperator that really just takes a whole bunch of x rotations and returns something that looks like a direct product of, tensor product of x rotations, which are possibly conjugated by unknown z rotations, which in general could maybe depend on whatever this x rotation happens to be. This is the definition we give in our paper, and we also give a bunch of sub-definitions for other types of gadgets. Specifically, you can see that, or at least we show in the paper, that there's certain types of QSP protocols which satisfy this definition. And it's pretty easy to find QSP protocols that sort of give you this property, namely the z conjugation, but it's sort of difficult to find ones that give you only this x to x mapping. So yeah, there's B output legs and there's A input legs, so there's basically A oracle slots, and this is acting on B sort of single qubit registers. And these psi sub j's tend to be polynomials in the cosine theta sub k's. Oftentimes we work sort of in the arc cosine of everything, and those are the x variables you see, but for this purposes, it's a little neater to notate it this way. Yeah, so this is, yeah.
Quick, could you go back? So this, the psi's are functions of the thetas?
Yeah, so
As I like change these, yes.
yeah, so as you change theta, sort of this psi will usually change very nonlinearly dependent on the theta, because this is the result of a superoperator. You can.
The psi's you choose?
No, the phi's here are something which just happens as a consequence of the superoperator. So we assume that maybe we can't control these.
Okay.
And it turns out that in QSP, oftentimes you can generate something that does this, but not something which gives you only x rotations. If you want a QSP protocol that takes an x rotation to an x rotation, it fixes uniquely. They're basically only the Chebyshev polynomials. And we would like to do things other than Chebyshev polynomials.
The tensor product is the key.
Well, right now they're just sort of non-interacting, right? So each register is doing things independently. But in general, each of these protocols could use, each of the psi sub j's could be a multivariable function of the cosine theta sub k.
Sorry, what is the size of B?
B is just an integer. That's just the number of registers. So you have B qubits, and you want to eventually have a circuit which operates on B qubits.
You're still talking about the cubitization.
Yeah, this is still with qubits. Yeah. So everything here is happening with qubits. Yeah. So the ways to think about this top picture is, these are three different representations of the same thing. So the first one is just direct substitution of circuits into spots where oracles would have previously been called. So this is like the technique that won't work, but maybe we're assuming through this theorem 2.1 that you can do something in between there, which allows this kind of direct substitution to work, and you would like it to achieve something like what's on the right here, which is direct substitution of polynomial outputs in polynomial inputs. And then finally, at the bottom, we have the superoperator notation, which is just a little bit more compact, and these slots now represent input unitaries and output unitaries, which can be said, right now they're being labeled basically by the angle of the rotation that they achieve. So because everything is now x rotations of the input and output, it's sort of easy to talk about the function that's directly achieved. Cool. So yeah, there's a lot of colors on the slide, and I'm going to replace it with a picture in just a little bit, but this is sort of the very laborious way to write it out. But sort of in order to build things out of simpler parts, we just need sort of a method for linking two things. And this theorem deals with the case of a generic gadget, which is arity AB, and what we call an atomic gadget, which is arity CD. And the atomic gadget is defined in a similar way to how a QSP protocol would be defined. And so the first gadget achieves some multivariable function on multivariable inputs. The second achieves some multivariable function on multivariable inputs. And in general, there are sort of many ways to link two boxes. You can permute the legs. You can plug legs into other legs. And you'd like that sort of legs that you plug, output legs that you plug into input legs to represent functional composition of those arguments, and legs which pass through either direction to basically represent pass-through of those variables. So it's not super illuminating to stare at this, but this is sort of how you would notate it. Sort of more concretely, this is the figure that was at the beginning. If I have two of these boxes and I plug in a particular leg and maybe perform whatever this correction procedure that's necessary to make the direct substitution work, the functional composition should respect what I expect it to. So basically, what we're using for the composite gadget, which is this G prime, is a description of the atomic gadget which is the CD gadget, and a certain number of black box calls to the result of running the previous gadget. So all these things are recursively defined. And sort of you'd expect that this is going to scale in the number of times that the outer QSP protocol calls its particular input oracle if it's plugged into one of the former gadgets. And it's also going to depend on this zeta term, which we're going to define previously. So it turns out that the zeta term always scales polylogarithmically in epsilon, and also inverse polynomial in this delta parameter. And maybe this scares you a little bit, but delta for our purposes is going to be able to be chosen as a constant. And so this is sort of not too bad scaling, but there's things to discuss here, which we'll talk about later. Okay, so you have the way to basically link these things together, and this leads to sort of a bigger statement, which is we really can think about these gadget assemblages in terms of the polynomials that they achieve. And this is that if you have some family of polynomials that happen to be achievable by atomic gadgets, so this is some family that I'm not explicitly defining, but assuming that we have some subclass of gadgets which are actually implementable by circuits that look like QSP, these are the atomic gadgets, and you assume that you have some big polynomial, which is big composition of all of these sub-gadgets, then you would, and that each of these polynomials has degree, which is polynomial in some integer in the sky, and the whole depth of this thing is only log in that degree, that the whole thing sort of has, as you'd expect, degree, which is polynomial in the degree of the polynomial that you want. A lot of times of saying polynomial, but basically here, you're not getting anything for free. If you're trying to recursively compose a degree d polynomial by itself n times, right, the scaling of that polynomial is going to go like d to the n. So you really don't want to compose these things too often. But we're sort of going to be using this as a stopgap to achieve functions which wouldn't have been obviously achievable with other methods.
What does the symbol serve? I-.
Yeah, so this is a bit of compression that I'm not talking about here, but it's very similar to sort of how this notation works down here. So up to sort of ways to uniquely plug legs into other legs. So you basically need to define a permutation on this interlink, and you need to define where the set of legs that are plugged into each other goes. So this z set, and the legs which are passed through forward and passed through backwards. But if you count these as sort of arguments of the function, so namely like these are the g function, its arguments are the ones that are being passed through to the second gadget, whereas these are the ones that are being passed forward, these are the ones that are being passed back.
So lots of things get compact
Yeah.
on the fly. So is there a way to understand this h, x, y, x and y are single variables just to see?
Yeah, so if this happened to be the two variable argument case, and we're sort of abusing the union notation here, so h would be this g sub k, the yellow g sub k, and then this would just be of f of x and h of y. So yeah, you have, say, in the z argument would be both f and g, which are being fed into the second gadget, and the output of the second gadget, this would be h. And then you'd have two inputs here, but we're suppressing multiple legs.
Have you told us how you're embedding one, passing one gadget into another gadget?
Yeah, so this mysterious black dot here, which is the correction procedure, is going to, what's going to allow you to do that? No, not how you do it, just that it costs polylogarithmically in the precision.
Sorry, so on the next slide you had this delta that needed to be, it was basically the separation from 0 and plus or minus 1. Is that just because you don't get these 2D invariant subspaces if delta is 0, or?
Oh, true. Did I have a 0 there?
No. I think I just mean that the cubitization procedure, you get sort of only a 2D subspace if lambda is sort of away from 1 or minus 1, right?
Well, this is just something that follows from the fact that you're block encoding the operator, so you already know some bound in its norm. The problem here is going to be that QSP has some problems with, I don't know, how I want to think of it as like gimbal lock, which is that when it's very close to the ends of its input range, sort of it's going to stay in a U1 subspace of SU2 and not do sort of nice things. So as long as we've, in the boundary conditions, we're sort of far away from them, yeah. Cool. Yeah, so this is a table just from the paper of sort of the types of things that you can achieve with QSP. And so this is not a statement of efficiency of being able to achieve sort of arbitrary functions, but it is a statement that you can sort of achieve all multivariable functions, possibly inefficiently using these methods. Namely, all of the things you can achieve with QSP and MQSP, these functions are achievable in terms of gadgets. These would be 1-1 gadgets. Then you have things like addition, multiplication, and scalar multiplication, all up to this basically norm constraint that you normally have, as well as a parity constraint, which is sort of standard in QSP. So when you're adding two functions, you're not really adding them, you're taking their average, and so on. And if you multiply it, you can only multiply it up to a ceiling function, et cetera. But up to that sort of mild constraint, you can do all of these things, and we write out explicit gadgets for doing that. Standard polynomial composition in one variable is obviously a subset of the generic gadget linking. And then sort of you can build these into a bunch of sort of smaller examples from things like bandpass functions and step functions and things like that.
If I combine two gadgets in these ways, do I get another gadget?
Yeah, so the family is closed under linking of legs, basically, yeah. So later we talk about there's a context-free grammar that defines gadgets. And so we know things about their syntax, and we know things about their semantics. Yeah, so this is just an example. This is probably a suboptimal example of how you would do this. With LCU, doing the sum is very easy. You just need an extra qubit, and you throw it on there. But you can sort of pull out all of the stops and think about these angles that basically take square roots, and then do these things which I call angle sum and difference, which are kind of a complicated Laurent polynomial, and things that take products, and basically use a bunch of cosine and angle identities to have something which really spits out basically the sum of two included variables. And it does it in a way that looks very different then. Yeah.
So in this diagram, how many qubits are you talking about?
These aren't qubits, sorry, these are superoperators.
And
yeah, if you do this, so it would end up actually using an extra qubit. So it's the same a number of qubits as LCU in this case. And this is sort of the argument that for low degree polynomials, it scales pretty similarly to LCU. But sort of the benefit of this method is going to be for higher degree compositions. But it looks very different than LCU. So it's not obvious, and I'll talk about this later, sort of the comparability of these methods in terms of achieving a desired multivariable block encoding. But we're just saying that sort of at this result, if you had two, and they gave you, you have these gadgets which you can use, then really these results here will just be composing the functions here. So if I had an E gadget that gave me a sum, and I had a different E gadget, and I computed the circuit that resulted from this, it would give me the function that results from composition.
So these like ABCD you have to construct by hand. These are sort of like.
Yeah, well, the ABCD tend to be simpler functions, but okay. Yeah, you would know the phases for each of them. But at the end of the day, you would tell your computer to compile me the circuit that gives me the output for a particular output leg with respect to a given set of input legs, and it would do it for you. But yeah, in principle, these smaller things are simpler and maybe have better performance. Or can be optimized, or maybe they come from some other property, and you just want to be able to stick them together at the level of the functions they apply without having to worry about, it'll tell you automatically what the extra space that's used is. Yeah.
You said these ABCD are gadgets from unitary to unitary mapping superoperators, right?
Sorry, what?
These ABCDs, they're like unitary to unitary maps, right?
They're approximately unitary to unitary, yeah.
Okay, so x0 and x1 should be unitary as well.
Yeah, so I'm abusing notation here. What I mean here is that the input is an x rotation by an angle arc cosine of.
So the total thing is going to be a rotation of x0 plus x1.
It'll spit out an x rotation, yeah, that is by 1/2 x0 plus x1. Okay. Cool. So yeah, the motivation for this work comes also from the world of classical signal processing. So oftentimes people were thinking about the design of so-called cascaded classical filters, and these are being used to, say, improve response functions for audio processing, or even in quantum cases as well. So a sort of suboptimal but interesting method for doing, say, fixed point amplitude amplification or Grover search comes from a method that looks very similar to a one-dimensional version of this. And there's sort of a lot of interesting literature on understanding sort of how do I well approximate a desired function via a short tower of recursively composed polynomials, and this literature is quite interesting just by itself, but is sort of gone by the wayside in the world of digital signal processing. There's also sort of single variable versions of both self-embedded QSP and QSVT, both sort of on the numerical side. There's a paper from Keisuke Fuji from the University of Osaka, as well as a paper from our group that considers sort of finding the complexity of doing this embedding as well as sort of whether it has nice properties.
What does embedding mean?
Yeah, sorry, what I mean here is just using a QSP protocol as another QSP protocol's oracle. So just recursively embedding that protocol into another one.
Just combine them.
In the single variable, as long as your phases are anti-symmetric, then you can automatically combine them. Yeah.
Which is the optimal thing to do.
What?
Which is the optimal thing to do.
Yeah, the optimal thing to do is just if the anti-symmetric phases. And this is specific to the QSP ansatz because the Z rotations are sort of very special. So yeah, in the single variable case, everything is understood very well, but in the multivariable case, right, not only do you need anti-symmetric phases, but you also need that the relative phase of the two oracles is the same, because this is what the normal QSP protocol expects. Yeah, and then also some work from functional programming techniques in terms of how do people normally think about higher order functions in classical computations, and things like referential transparency. And I don't know if people here are into functional programming languages, but there's a lot of nice properties that you'd want out of being able to create superoperators like this, sort of as first-class objects. So yeah, the correction protocol, at a high level, it's sort of very simple, and there might be sort of other ways to do this, and there'll also be some caveats as to how efficient this is. But the idea is that you want to use the output of a QSP protocol in an oblivious way to sort of cancel what's wrong with that protocol. So the good thing is that everything here is sort of unitary, so you don't have to worry about sort of stochastic issues. But let's say that I have some protocol here which looks like a conjugated X rotation. So it's an X rotation that has some unknown Z phase. And let's also maybe assume that this X rotation is far from being the identity at so the interior rotation is far away from having X equal to plus or minus 1. Then we use this protocol to generate basically something that looks like twice the Z rotation. And then we do something which looks like a very simplified version of fractional query methods, which are made easier because we know everything about the basis of this function to recover something that looks like just the original X rotation. So a lot of this looks very similar to amplitude amplification, and it scales similarly. So basically, as long as the norm of this function p is bounded away from 1 and minus 1, then sort of the convergence to what we'd like in this circumstance happens sort of exponentially. But yeah, you can also think about it, on the single qubit level as just sort of replacing q with something that really looks like the principal square root of 1 minus p squared. And then sort of a high-level diagram of what's going on. So p is sort of the original protocol here. It's being fed into something that looks sort of like amplitude amplification with arrow 1, and it's also being fed at the very end to something which is being conjugated by these correction operators w, and then in the middle here you have something which looks like basically a coherent switching between two QSP protocols, which allows you to have approximate controlled access to v, which allows you to get the square root. So there's sort of 3 steps, and there are cases where some of these steps are bypassed, and where you don't have to use additional qubits, or you can sort of get away without doing as dramatic of an amplitude amplification, but that's sort of not the focus here. In the worst case, you really do have to go through these steps. At the end of the day, you get a P protocol, which looks like an approximate X rotation, and you haven't had to measure anything, and the extra qubits can be freed.
So this gets rid of the Z's on the lines.
Yeah, it gets rid of the unknown conjugation.
Is that the purpose?
Yeah, that's the purpose of this whole method. Yeah, so costs, there are some questions here, especially because oftentimes, especially these low-degree gadgets, it seems like we're spending a little bit more than we should. So the problem at plus or minus 1 is you'd expect this means that the angle is approximately 0, which means your QSP protocol basically just looks like a Z rotation no matter what you do, and this is bad for your purposes. So assuming that all your functions are within these sort of bounding boxes, this is a property that's preserved under composition and all the algebra that we used before. So this delta really can be treated as an order 1 constant. But it will enter into the complexity depending on the depth of the gadget network you look at. So at the end of the day, we really do want to consider pretty shallow gadget networks. But everything will be sort of polynomial in the parameters as you'd expect. And this polylog 1 over epsilon term is an error that is on the same order of the one that you get from standardly approximating a smooth function with a polynomial approximation. So it's maybe polynomially worse than optimal, but I'll talk about sort of the question about what we mean by optimality in a second. So yeah, in general, a gadget, right, computing its cost is not there's not a single number, right? This thing has B outputs and A inputs, and so you have a cost for each output leg with respect to the query complexity to each input leg, and this is a cost matrix C. If people want to look at it in the paper, there's a very nice way to just compute sort of the composite cost object in terms of the sub-gadgets cost objects, and it looks basically like matrix multiplication with some row padding. But these query complexities, these can sort of break into cases. And in the single variable case, right, everything is handled by the antisymmetric phases. In the case that you have positive semi-definite Q, which is still a relatively large class of functions, you don't need to use any extra space. And under some sort of slightly stronger assumptions of access to controlled versions of special unitaries, you can also get rid of introducing some extra space. So we sort of break down to a series of tables under each of these assumptions and when they might be reasonable, sort of what the cost of this type of composition would be. So yeah, the big question is, is efficient? Can you do this in other ways? Or in bold, like why not just use LCU? It seems like this is what LCU is really great for. And the thought here is that LCU is great, but LCU is not specifically for spectral mapping. And so if you really only care about a fixed eigenbasis, it seems like maybe you should be able to do a little bit better in certain cases because we don't need to make such strong assumptions on the variety of operators that we might need to combine. But really for the gadget networks we care about, we need them to have polynomially many, polynomially size in terms of their generalized degree, so the degree with respect to any query input, and we really need log depth, so you can't sort of go crazy on these operators. But the good thing is that we maintain all these nice dependencies on the infinity norm versus say the one norm, and there's no post-selection in our method, although maybe you can argue that we do some amplitude amplification implicitly, so the post-selection is sort of being placed into another area. And we have this nice modular property that you can sort of reuse these filters, and you can know everything about their cost and the cost of the assemblage simply in terms of the cost of the pieces. So there's very little sort of boilerplate going on in combining them. But yeah, really where this method sort of helps is in linking high degree gadgets where LCU seems to sort of scale non-optimally in certain parameters. But the cost of these gadgets now, instead of being coupled to, say, the number of terms or the degree, is coupled to things like questions in polynomial decomposition theorems. So given a given function, what is the best approximation to that function, which is a composition of depth 3 of polynomials? And there's a lot of literature that actually talks about this question that's very interesting and which I won't get time to talk about here. But people have all sorts of nice, efficient methods for finding such approximate polynomial decompositions. It was actually believed to be a cryptographically hard problem at one time in like the 80s, and then everyone found a bunch of good algorithms for it. So I don't know, win-win, I guess. And the last thing is that this is not really in competition with LCU, right? Both of these are striving to create block encodings and can probably use these block encodings in black box ways. So if there's some sort of sub-gadget that you'd like to create, which is better created with LCU, you can stick it in here. So our method never does worse than LCU, but it's worthwhile to see where it can do better. And so sort of let me start by saying that this table is one way in which you could try to compare LCU and gadgets. There are many ways because we have a separate property that they don't use, which is this same modularity of given transforms. But sort of for a paper that I'm referencing here, which is about multivariable quantum eigenvalue transformations, sort of if you do it in the most naive way, and there are probably some methods that people know about here that can shave off this, and I'll say that a lot of these polyfactors are usually low-degree polynomials. I'm just keeping this really general. But the number of queries, in QSP, you'd like it to scale just as the degree of the achieved polynomial versus something which maybe depends on both the degree and the number of variables. And the space here may also grow sort of either in the number of, the space should grow. I think I'm missing a polylog factor. Anyway, the space that we use for a given gadget is constant, whereas it should depend sort of logarithmically on the number of terms in LCU. And then in general, you have sort of dependence on 1 versus infinity norms. So there's some questions of how expensive the post-selection is in LCU. We also have some special cases where the number of additional qubits beyond those for standard block encoding needed is 0. So yeah, and then I'll sort of finish up, I think, a little bit with some discussion about topics in functional programming. So oftentimes when people care about programming languages, they care about syntax and semantics, so the study of meaning and the study of structure, or conversely sort of grammar and again, sort of intrinsic meaning. And one way of viewing this work is the construction of a monad. And this is a bad definition that people like to trot out because I don't think it really answers anything. It's a monoid in the category of endofunctors. But really, it's just a way of taking values and wrapping them with some additional information, which can either keep track of side effects or sort of things that you might otherwise want to keep track of in a computation. But the problem here is that QSP sort of naturally seems to wrap up types. Say this type here is a scalar value or something contained in an X rotation. You suddenly get side information in the off-diagonal terms. And what you'd really like is sort of what they call the bind function. And this is basically the standard binary operation in the monoid. And this bind operation basically takes the description of something which maps the unwrapped type to the wrapped type, and a wrapped input unwraps the input, applies the function, and rewraps it. And sort of this helps you design things like control flow and have things like referential transparency and all sorts of nice things in declarative programming languages. So in the sort of depths of the appendix of our paper, we talk about sort of attribute grammars, which are just define the syntax of these gadgets, as well as sort of a full description of their realization as monadic types, which describes their semantics. These two things are not totally separate in the world of programming languages, but at least in our case, you can sort of nicely describe things. So last thing, we have a Python package, and this sort of allows you to construct these things and compute their query complexity and their output functions and sort of understand their behavior. And this is still in development, but all of its major features work. So if you want to submit pull requests because something is broken, please let us know, because I'm sure there's something. And then finally, so another nice thing about this package is that it can sort of programmatically spit out Tix figures for the gadgets, as well as other sort of visualization techniques. So we try to make it as friendly as possible for people to understand these objects. And so for the final topic, just things to take home. So under the assumption that you have relatively large degree gadgets, and you have that a function is well approximated according to these polynomial decomposition theorems, it seems like in a lot of cases you can do a bit better than what naively LC would allow you to do in terms of multivariable block encodings. And it really allows you to think just in terms of the functions that these superoperators are applying and snap them together in a pretty simple way. So there's questions of efficiency and also questions of ease of use, and we have something to offer on both of those sides. Another thing that I think is sort of interesting independently, whether or not it ends up being sort of useful past here, is the coherent use of the output of things that look like QSP or QSVT by other things which look like QSP or QSVT. So these algorithms can sort of treat themselves in interesting ways and perform nonlinear transformations because everything is in a nice sort of unitary model. And I think that there might be sort of interesting work. There's already some stuff on so-called algorithmic error correction that does sort of a similar effect. And I think that's it's an intriguing idea. Finally, we have this repo, and then a whole bunch of stuff in the appendix about some connections to some stuff in programming languages and trying to address some of the needs that the community is out there in terms of what is a reasonable idea of a quantum data type or a certain sort of programmatic verification or compilation of things, even an interesting subclass of quantum circuits. So this is not a quantum programming language, right? We're dealing with a very restricted subclass of circuits, but it has a lot of nice properties that are common in functional programming. And the final thing, just there's some interesting sort of ancilla-free gadget subclasses, which I think are quite interesting from a resource point of view, and it's not so clear sort of what the right functional description of the subclass is, and so if people are looking for an open question, we try to describe that in the paper. But hopefully a little bit under time, but that's it for the moment.